Right, good morning. So today we are looking on the second part of magnetic fields, where we want to measure the magnetic field strength B using a current balance. So we are going to explain two methods that we can use to measure that magnetic flux density B. So this one, we have this setup where we are referring it to the current balance. So for the current balance here, we must have these two pivots, where we are saying the knife edge pivots, and we must have a slab of magnets where these two poles are going to produce this magnetic field. The one we want to measure is density B. So what we are going to do, we are going to have this rectangular wire which is connected to the circuit, which is not shown in the diagram, and we are going to allow current to flow. As you can see, current is flowing in this direction, and using Fleming's left hand rule, if we switch on the current, this part of wire is going to experience a force. In this case, using the left hand's Fleming's rule, the force is going to move downwards. So if it is moving downwards, it is going to cause what we call the clockwise moment. So for us to find the value of beta, we are going to use this formula. F is equals to B I L sine theta, but we are going to assume that this section of the wire is placed perpendicular to the magnetic field, meaning to say our theta will be 90 degrees, hence we have this one. So for us to find the value of B, if we make B the subject here, we are going to say that B is equals to F over current times the length of the wire which is inside the magnetic field. Like in this case, this is the length of the wire which is inside the magnetic field. So we can measure the length. So for us to get B, we can measure the length, we can get it. Then, like what I have said, this section is inside the magnetic field, but this wire is connected to a circuit which is not shown in the diagram, but that circuit we can measure current using the ammeter, so we can find the value of the current. So for us to find the force, this force, we are going to use these weights which are going to balance this magnetic force which is causing the clockwise motion. So if we put the weights here, they are also going to make the anti-clockwise motion this direction. So we are going to use these weights to find the value of this force where it balances, meaning to say, if we find the mass at which it balances with this force, suppose that mass is m, and if we multiply by the gravitational acceleration, we are going to get the weight that is going to give us the force which balances this magnetic force. So meaning to say, if you want to find the value of B, we are going to use the mass which we have used here in order to balance this magnetic force which causes this clockwise motion about these pivots. So meaning say our F is equals to mass, the one that balances force, times the gravitational field, that will be the weight, then times a current we have measured, then the length, then we are able to find the what? the magnetic density. So like what I have highlighted earlier, we are saying a pair of slab magnets provides a uniform magnetic field. When a current is passed through the rectangular wire via these knife edges, the balance is deflected down in this direction and causing the clockwise motion. The deflecting force can be found by balancing the wireframe using small weights like what I have highlighted. The strength of the magnet can be calculated using this force over current times length, where the length of the conductor in the field of the wire. So this one is the first method. One can use this method to calculate the magnetic flux density. So the other way now, we can use this setup where we are saying we have this setup where we have the magnet and the wire. We have part of the wire which is passing through the magnetic field, like what we have indicated earlier. For us to find the current flowing into the wire, we have to connect the ammeter here to the circuit, such that if we close this circuit, we are going to measure the value of current here. So in this case, we can find the value of current. Then for the length of the wire, from here to here, let me redraw again. The length of the wire is within this section, so we will measure this length. It represents the length of wire, and we are going to assume that the wire is placed perpendicular to the magnetic field. So meaning to say our theta is 90. So we have the formula F equals to BIL. And if you make the subject, since we have I, we can measure current using the ammeter, and you can also measure the length of the wire. So in this case, as you can see, before we close the circuit, we are going to have the reading. This reading is the mass of the magnet. But the moment we are going to close this circuit, current will start to flow, and according to Fleming's left-hand rule, if the current starts to flow in a conductor, it is going to experience a force, and Fleming's left-hand rule gives us the direction. Like in this case, maybe if the force is going to be experienced upwards, there's going to be a change in the scale. So initially, before the current moves, we've got this mass, right? Then if we close the circuit, we are going to see a change in mass, either an increase or a decrease. But this change in mass is going to be caused by the force on the conductor due to the magnetic field. Meaning to say, if the force is upwards, according to Newton's third law, there is going to be experienced a force in equal but in the opposite direction, the one that I've indicated downwards. So those forces are going to make the scale to change. So the reading can increase or the reading can decrease depending on the direction of the force being experienced by the wire. So if we have the final reading, we must find the change in mass. So the change in mass we are talking about is the difference between the final mass and the initial mass that we have here, and that change in mass is the one which is caused by the force experienced on the conductor due to the magnetic field. So you know, force is weight. So if we have that change in mass, and if you multiply it with the gravitational acceleration, we are going to have our weight. So it will be the value of F here. So it will be change in mass times gravitational acceleration, then divided by current over length. Then we are able to find the value of what? Of a flux density. So let me just go through here. So we are saying the current balance relies on the Newton third law, like what I've said. Not only does the magnetic field cause the force on the current causes an equal sized force on the magnet, but in the opposite direction. So the difference in the reading on the top pan balance when the switch S is closed, open and closed, gives the measure in the electromagnetic force. Then we have to punch it into our formula. Then we are able to find the value of the magnetic flux density. Right, so now moving on, we are moving on to the next concept. Like in this case, we want to find the force on a charged particle moving in a magnetic field. As you can see in this diagram, we have the direction of the magnetic field with a strength of B, and this one is the conductor, and here is the direction of the current, and here is the direction of the force. You can pause this video and try to use the Fleming's left hand rule to see if it is the correct direction of the force. So in general, from O level, you know, you must know the direction of current flow in relation to the direction of the electron flow. They flow in opposite directions. If the current is flowing from left to right, then your electrons will be flowing from right to left. They oppose. So this is the direction of the current flow, but in terms of electrons, they will be moving in this direction, opposing the current. So as you can see, this whole wire is going to experience a force. So if the wire experiences a force, it also implies that these electrons, these charged particles, they are also going to experience a force, and we want to come up with a formula for that force, and we have to show that that force is equals to what? Is equals to B QV. You know, from the calculations that we've done before, the force experienced on a wire is F is equals to B, the flux density times current, then times the length of the wire. That is the force being experienced by the conductor, assuming that the conductor is placed perpendicular to the magnetic field, meaning say our theta is what? It's 90 degrees. So our sine 90 will be 1. So from the definition of current, you know, charge is equals to current times time. And if you make the current the subject, we are going to see that your current is going to be so if you make the current the subject, we are going to see that the current is equals to charge over time. That is, current is the rate of flow of charge. Then we are going to substitute into our formula. Then we are going to have our B, where there is a current. We are going to substitute with what? With Q over T times L. Then if we rearrange the formula, you are going to see that this one is B Q, then L over T, right? Then if you look closely on the diagram, L is the length of the conductor, that is the length which is going to be traveled by the electrons here, and the time taken. So we are going to have a quantity which represents length, distance traveled over time taken, which is the speed, the one we are indicating here, the speed of those electrons. So it will be a B, a Q, V, where our V is going to be the speed of electrons. And also from the definition of charge, you know that charge is given by what? Charge is given by number of those electrons times the electronic charge, the elementary charge. So if we are going to replace here, we are going to get our magnetic flux density, then number of electrons times that charge of an electron times V. So since we want to look to find the force on an electron, which means we have one electron, our n is equals to 1, we are going to see that the force on the electron is going to be B E V. That is the force experienced by an electron. So in this case, if we don't have an electron, maybe we have a proton or any charge, maybe an ion or a helium or whatever. So this will be our general formula. The force on that charged particle is equals to the magnetic flux density times the charge of that particle and times the velocity of that particle. That's how we find the value of what? Of the force. Or we can use this formula, you know, from a current in DC circuits, that current is also NaQV, where we say N is the density of charged particles, then A is the cross-sectional area, Q is the charge on an individual charge carrier, and V is the drift velocity. So from this definition, if you make your if you go and substitute your current where there is current, you are going to get this expression. This one is the current. Then you can factor out Q and you can factor out V, and you are going to remain with density times volume. AL, it represents density times volume. AL is the volume, then times the density. It gives us the total number of charged carriers, which is N in the conductor. So the force on those N charged particles, it will be BQ NV, meaning to say, if you want to find the force on just a single charge carrier, we are going to use N equals to 1. Hence we are going to get the same result, that is the force experienced by a charged particle in a conductor. And you also need to remember or to recall that here our assumption was that the current, the wire is placed perpendicular to the magnetic field, but sometimes it may be placed to the field at an angle of theta. Make sure to multiply with what? With the sine theta. So it will be F is equals to BQV sine theta when the wire or conductor is not perpendicular with the field. So you need to take note of that. Here we have a worked example here. We have a proton traveling horizontally at a speed of this one, meaning to say this one is our speed v, enters a uniform magnetic field of strength 300 milliteslas at an angle of 40 degrees to the field as shown in this diagram, as you can see. So this one is our B, the magnetic field density. So the force, we are going to use this formula because it's not perpendicular. So we want to calculate the force on the proton and also state the direction of that force. So our answer, like what I've said, we are going to use the one with the sine theta. That is our BQV, meaning to say this one is our B, 300 milliteslas times sine theta first, then times our charge of the proton, then times the velocity. We are going to get this force. And for the direction, let me always refer to the Fleming's left-hand rule, where we are saying here the first finger represents the magnetic field and it points downwards, as you can see from the diagram, and the second finger shows the direction of the current. The direction of the current here is from left to right. Why? Like what I said before, the direction of current is in the opposite direction of the electrons, and you know electrons are negatively charged, but here is a proton. So a proton is in the same direction with the current. So that's why we are saying the current is from left to right. And also the force to be pointing towards the paper by using the Fleming's left-hand rule. It's always pointing towards the paper. Right, so looking on the other. Right, so our next concept is on how we can measure the charge to mass ratio of an electron. In this case, it's an electron. That's why we are saying E over ME. So if we are also required to find the charge to mass ratio of any charged particle, we'll be using Q, charge of that particle, over the mass of that charged particle. So this relation is what we are referring to charge to mass ratio. So in this case, we are going to demonstrate on how we can find the charge to mass ratio. So this one can be found when we make electrons to move in circles, like using a fine beam tube filled with gas such as hydrogen at low pressure. So this one is the setup. In this case, this gray shade or region represents the uniform magnetic field which enters the paper. Like the way we are seeing this plane, we are saying our magnetic field, the direction of that field enters the plane of the paper, represented by this X. Then we are also going to have the electron gun, which is connected to the anode with a positive of V, that is the voltage supply. So meaning to say this electron gun is going to emit electrons which are going to travel at speed V, but the direction of the electrons will be in circular path. So electrons are accelerated by this anode, and from this, when we are saying electrons are accelerated, what we are simply saying is that electrons are given energy. And you know, from the definition of voltage, you know the voltage is work done. It's work done per per unit charge or per charge, mean to say here since the charge is an electron, so we say work done, the voltage is work done over the electron. Then if you cross multiply, you're going to see that the work done on the electron will be that charge of the electron times the voltage supplied. And we are saying this work done is going to be converted to kinetic energy. It is going to be converted to what? To kinetic energy. That's why we are seeing the electrons from the electric gun now moving in a circular motion. So if they are moving, they've got velocity. If something is moving, the velocity, it has got kinetic energy. So from the conservation of energy, that work is converted to kinetic energy. So let's see what happens next. So like what I'm saying, from the principle of conservation of energy, this one is now the kinetic energy is equals to this work done, which is converted. So we have our equation 1 here. Then where m is the mass of the electron. So the mass of the electron, the electrons that experience a force, the electrons will experience a force BQV. So our Q is E in this case at right angles in the direction of travel. So let me go back a bit. There are two equations that we can use them. So like what I said earlier, these electrons will experience a force due to the magnetic field, and that force due to the magnetic field is what we are referring as to a BEV. But since the electrons are moving in circular motion, there is what we are referring to the centripetal force. This one is the force due to the magnetic field. We also have the centripetal force, which is is the mass of the electron times V squared R, the radius of the circular path. So if we equate the two, from F is equals to MA, F equals to MA, where we are saying this one is the centripetal acceleration since it's moving in a circular path, and this force is the force due to the magnetic field. So we are going to see that if you multiply BEV is equals to this one due to the centripetal force, it's mass of the electron, then the velocity squared over R. Please don't confuse yourself with the velocity and the voltage. Our voltage is a capital letter V. So from this we can see that one of the V's will cancel out, like this V, it cancels with this one of this V. And if we are going to make E over M the subject, we are going to remain with E here, then take M to this side, then we are going to have the mass of the electron. So this case we will have V over BR. So the charge to mass ratio of an electron is that velocity divided by the product of the magnetic flux density and the radius of the circular path in which the electrons they are going to move. So it's another way, or it's another formula where we can calculate the charge to mass ratio of an electron. If we have the velocity, if we have the magnetic flux density, and if we have the radius of those circular paths, So one can use this one. You still remember from equation 1, we have this equation where we are saying, like in this case, we want to derive another formula for charge to mass ratio of an electron as this one. We can also use this one. So we want to find where this is coming from. As you can see here, we now have the voltage, not the velocity. So we need to eliminate V. So as you can see from here, this one is our kinetic energy. This one is our kinetic energy converted from the work done on the electron by the voltage supply. So this one, I think we are together from here. And still remember these two equations, I equate them this one, right? So from here and here, this is where we are going to eliminate V. We can eliminate V in this case. We can eliminate V by using equation 1 and equation 2. So let's say let's make V squared the subject. So our V squared from this equation, we are going to get 2 EV. It's 2 EV over the mass of the electron. That is going to be our V squared. And if you want to find the V, maybe we are going to say the V is going to be not that capital letter. Let me write it in terms of small. Maybe one may think it's velocity, it's voltage. So let me say, if you want to find your V velocity, it's square root of, it's going to be the square root of 2E V voltage over ME. Mass of the electron. So let's go and substitute here. As you can see from this equation, BeV is equal to the mass of the electron times V squared over R. In this case, these V's can cancel. This V can cancel, and you can remain with B. E is equals to M ME, then V over R. Then where there is V, we are going to substitute this value. So this equation is going to be BE is equals to our ME over R, then times our V, which is square root of, which is our square root of 2 EV everything over ME. So from this, now let's try to remove the square root, because we don't have the square root here. Let's try to remove the square root. So we are going to square both sides. Let's square both sides. If we square this side, we are going to get b squared e squared is equal to m, the mass of the electron, squared over radius squared. If we square this one, the square root disappears. Here we will just have what is inside the bracket, 2ev divided by me. We can simplify this. If you can see here, this one is, we have an e here, so this e is going to cancel with one of this e, and this m here is going to cancel with one of the m. So here we are going to remain with e, and I'm going to take this mass to this side, so it's like dividing. And here I'm going on top, here I'm going to remain with 2 times the voltage, this it's a capital letter voltage, over, already I have r squared here. Then I'm going to take this b squared down here, so it's dividing. So this one is also another formula for calculating the charge to mass ratio of an electron. This is the one that we are supposed to show. So one can use this one, that is if you are given the velocity. But if you are not given the velocity, you are given the voltage, you can use this one. So for the worked example here, as you can see, find the ratio of the electron in the following result, from that following result. So here we are given the voltage, we are given the flux density and the radius, meaning to say we are going to use this equation, and as you can see is the one which is being substituted. And if you calculate this, make sure to convert everything in terms of SI units. Milli, it's times 10 to the power of minus 3 then squared. Then this one to meters, you multiply by 10 to the power of minus 2 then squared. Then you are going to get this value. It's from the results, but the true value is this one. I mean to say the two values, they are very close. This one is a good estimate. Right, so that's how we find the mass, the charge to mass ratio of an electron. That's how we find the. Right, our next concept here, we want to separate particles with different velocities when they enter into a magnetic field. So the first thing we need to do here is to have the uniform magnetic field set at right angles to the uniform electric field. So if we have these two fields, like in this diagram here, we have these two parallel plates, the positive and the negative, and the distance between the two. This will give us the uniform electric field. Maybe the direction is not drawn here. Maybe I can indicate maybe with the just two lines. This will be the direction here of the electric field. this will be the direction of the electric field. So it is going to be set at right angles with the magnetic field. So those axes, the axis is representing the uniform magnetic field into the paper, right? Then this one is the uniform electric field acting down the paper. So there are two fields which are at right angles to each other. Here we have a beam of positively charged particles moving with different velocities. Here. So we want to find those or of velocity of those particles which are going to be undeflected. They are going to just pass through horizontally through this one. So we are going to select those particles that are going to just pass through, meaning to say they are not going to be deflected. So the positively charged particles moving with different velocities enters this uniform field, magnetic and uniform electric field, as shown in that diagram. The magnetic field is going to exert a force, the one we are saying VQV, the magnetic field, and that direction of force is being experienced or being experienced using the Fleming's left and rule. So this will be the direction, but at the same time we have the electric field is also exerts a force from electric fields. Recall from electric field that force is equals to QV over D, and it also moves in the direction of the field, which is downward. So these forces, they are going to cancel out. So if this force is equal to this force, this object might appear stationary. It will be in terms of down and upwards, but it will be moving horizontal. So it is going to be undeflected. It's not going to be deflected. So meaning to say, if you equate those two forces and make your V the subject, you are going to see that the V, the velocity of undeflected particles, is going to be the voltage across the plates divided by the product of the magnetic flux density and the distance between the two plates. So from that voltage, we are going to see that if the particles are going to move, or if we impose particles which are going to move at a speed greater than this V, the particles are going to be deflected upwards. The particles are going to be deflected upwards. Then, mean to say they will move in this direction. Mean to say they will move, those particles, they are going to move in this direction. They are going to be deflected upwards, which means if their velocity is greater than this V, the one we have calculated there, then if the velocity is less than this one, the particles, they are going to be deflected downwards. It will be, say it's V2, it will be less than V. So that's why we are saying if particles traveling faster than this velocity, they will be deflected upwards. But if particles are slower than this deflective, it will be deflected downwards. So generally, the above experiment illustrates how particles moving with the different speeds can be selected. So on our next lesson, we are going to look at the Hall effect and the Hall probe, how the two relate each other. So see you in the next lesson.